Hello and welcome to my presentation on optimizing a generic function in SAT. This is the agenda for today's talk. First, I'll provide some background about optimizing a generic function in SAT, the problem we're going to handle today. And then I'll talk about polarity fixing in SAT and anytime maxsat, which is essential for the algorithm presented later. Then I'll talk about the Polosat algorithm for OPSAT, which is the main contribution of the paper and this talk. And then we'll talk about experimental results. How Polosat helps, anytime maxsat, and an industrial placement application. Here's a quick reminder about the SAT problem. In SAT, given the propositional formula F in conjunctive normal form, the solver should return a model to F or prove that none exists. In this example, we have a formula F here with three clauses, and it has three models. And the SAT solver should return any one of the three models. So there is no significance to which model it returns. It's free to choose any. Now I would like to extend SAT to optimization. In the so-called OPSAT problem, in addition to F, the proposition formula F, the solver is also given a pseudo-Boolean objective function psi, and it should return a model to F which minimizes psi. So now the model matters. A pseudo-Boolean function is just a mapping from every full assignment to a real number in the more generic form. So if we extend our example to have also a pseudo-Boolean function, then so we can check here the values for every model. So it's 86 for M1, it's 95 for M2, and 100 for M3. And M1 is the best model in our example because the value of psi is minimal. When it comes to solving OPSAT in practice, it is very important whether the objective function is a linear function or not. If it is linear, we can just use an off-the-shelf maxsat solver because maxsat is essentially the problem of optimizing a linear pseudo-Boolean function given the CNF formula. But what if it is not linear? What if psi is not linear? So one possibility would be to linearize psi and apply maxsat. But there are several potential problems with this approach. First of all, although it is possible to linearize a given pseudo-Boolean function if it is in algebraic form, the performance of such a flow is unclear. I'm unaware of any publications on the topic which solve an actual problem with linearizing psi. And then psi might also be a black box function. For example, a function which is calculated every time for every full assignment by applying some external program like a simulator. Then you cannot linearize psi at all. And our main contribution is the Polosat algorithm for solving the generic OPSAT problem. Now we are going to talk a bit about polarity fixing because this is a useful technique we are going to apply for implementing Polosat. So let's consider the following problem. How to make a CDCL SAT solver look for a solution near a given assignment A. So instead of invoking a SAT solver to get any solution, we wanted to return a solution near as close as possible to a given assignment. Okay, so here again, let's recall our example. We want to find a model near the assignment A, which assigns 0 to every variable, assigns false to every variable. By near, I mean minimizing the Hamming distance between A and the actual solution. And in this case, M1 would be the desired outcome. Because the Hamming distance between M1 and A is 1, it's 2 for M2 and 3 for M3. Now, there is a very, very simple method for modifying the CDCL SAT solver to look for a closed solution. One has just to fix the polarities of all the variables to A. It means that we do not change the CDCL SAT solver except for its polarity selection strategy. Whenever a variable V is chosen by the variable decision heuristic, the value AV is chosen as its initial polarity. And that's it. A very simple modification, but despite its simplicity, it works well in practice. So we are going to use this technique. Let me recall the definition of the maxsat problem. So essentially, maxsat is about optimizing a linear pseudo-Boolean function in SAT. On the input, the maxsat solver receives a set of the so-called hard clauses, which must be satisfiable, and the solver must satisfy these clauses. But then there is also the so-called optimization target, T, which is a bit vector consisting of literals, and each literal is associated with an integer weight W. On the output, the solver should return a model M which satisfies all the hard clauses, and in addition, it minimizes the weight of the satisfied target bits. So essentially, you want to satisfy as many target bits as possible, the value false, and the weight should also be taken into account. For example, let's again extend our example to maxed. So there is the optimization target T here, which consists only of A and B. And given the weights 2 assigned to A and 1 assigned to B, M1 turns out to be the best model because its value is 1, the value of M2 is 2, and the value of M3 is 3. So this is an extension of our example to maxed. Let's talk a bit about anytime maxed and the usage of polarity fixing in anytime maxed. So anytime algorithm is an algorithm which is expected to find better and better solutions the longer it keeps running. In the case of maxed, an anytime maxed solver is expected to output improving solutions all the time, and the SAT-based anytime maxed solver is using a SAT solver in order to improve the best solution so far. So a SAT solver is applied all the time, and sometimes it succeeds in improving the best solution so far. Now, polarity fixing is an essential component of modern anytime maxed solvers. There are two strategies, polarity fixing strategies I would like to remind you of. The first one is the so-called conservative polarity fixing, which fixes all the polarities to the best model so far. So say you found the model M, and then whenever a variable V, any variable V is picked by the variable decision strategy, its value in M is always chosen as its first polarity. And this simple approach allows one to find the next best solution faster, because essentially it carries out a local search near the previous best solution. And it turns out to be helpful in practice. And then there is also the so-called target optimal race conservative, or TORC, polarity fixing, in which the non-target variables are fixed to their best model so far, similar to the conservative polarity fixing, but the target variables are fixed to 0, so they're fixed to the ideal solution. And this is done in order for the first and any subsequent model to be as close as possible to the ideal solution. And this polarity fixing strategy turns out to be quite efficient, and it's applied in the winner of the Maxed Evaluation 2019 in weighted incomplete categories. Now it's time to talk about our main contribution, the Polosat algorithm for solving OPSET. I'm going to present you the Polosat algorithm. In my presentation here, I will assume that psi is strictly monotone in T, which means that whenever a bit Ti in T is turned off, that is when it's flipped from 1 to 0, psi is decreased. And this is a reasonable assumption for many applications, including maxed. So apparently in maxed, when Ti goes down, so it's flipped from 1 to 0, then psi goes down too, right? Now, a generic version of Polosat is presented in the paper. I'm not going to cover it today. The idea behind Polosat is to simulate local search with CDCL SAT solving using polarity fixing. Polarity fixing by itself simulates local search because it makes the SAT solver to look for a solution near a given assignment, but we want to take this idea one step further. Here is the algorithm. Polosat receives f and psi on the input. It invokes a SAT solver first, and then it runs a loop until M is not improved anymore. So the algorithm is essentially incomplete. It works until a fixed point. Each iteration of the loop goes over the bad target bits, where a bad target bit is a bit which has never been assigned 0 in any model, and it flips the current target bit. It tries to flip it by applying a SAT solver over F and not T as an assumption. So it tries to find a new model which has never been found before, because T has never been it has never been 0 in any model. And now a crucial part of the algorithm is that it uses a conservative or TORC polarity fixing. let's assume for a moment is conservative. So in addition to flipping t, the conservative polarity fixing assures that the algorithm is looking for a solution near the previous best one. Essentially, we are applying a local search, and we also guarantee that if we were to find the model, it will be a new model, right? So that's the idea. Now let's go back to the loop. If we succeed to find a better model, we update M. Otherwise, we just go on to the next target bit, to the next back target bit. And so that's the algorithm. We are using the torque polarity fixing in the paper in the actual implementation, but I'll be using the conservative polarity fixing in the example, which follows in the next slide for simplicity. Here is an example of polosat invocation. We have the input on the right-hand side. We have the same formula f we have already seen, and the same function psi, which serves as the objective function for our example. And here psi is strictly monoton in t, and we assume that t consists of all the variables for the sake of this example. And let me remind you that there are three models to f, and the models are colored by the light green color here. So the three light green entries are the models. The algorithm starts by invoking the SAT solver, and let's assume that the SAT solver returned the worst model 111. And actually, it is a reasonable assumption to make if a conservative polarity fixing is used, but it would have been probably impossible if torque had been used, because torque prefers to assign zeros over ones. So it would probably return the best model, not the worst one. But let's assume here that the conservative polarity fixing is used. Then it enters the loop. All the bits are bad because all of them have been assigned one. So the algorithm has to choose which target bit to flip. Let's assume it's A. It flips A, and the only model in which A is assigned 0 is essentially the best model, 0, 1, 0. So the best model so far is updated now. And B is the only remaining bad target bit. So C went from 1 to 0, so it's not bad anymore. A went from 1 to 0. B is the only remaining bad target bit. So we flip it. And once we flip B, the SAT solver has to return the model 101, because that's the only model in which B is assigned 0, but it does not approve the best model so far. So we don't change it. We don't update them. Then the algorithm goes to the next iteration of the loop. The only remaining bad target bit is B, because it has never been assigned 0 in any model. The next iteration of the loop flips B, and then it finds the model 101 again, because that's the only model in which B is flipped. And that model does not improve M, does not improve the best model so far. So it goes to the next iteration of the loop, but it does not enter it because M hasn't been improved, the optimal model has been found, and we are done. So we are done here with our example. Let's go over Polosat properties. It's an anytime algorithm because it invokes a SAT solver many times, and in many cases it succeeds to improve the best model so far. It is SAT based and it's incremental under assumptions, similar to SAT solver. So you can provide it a bunch of additional assumptions, which are then provided to the SAT solver. I haven't showed it in the algorithm, but it can be easily modified. And because of that property, it can be invoked instead of SAT in any time optimization flow. For example, in anytime maxed. So you can just take out all the SAT invocations and use Polosat instead, which is really convenient for integrating Polosat. So the integration is really simple and straightforward. It's easy to implement because it's a loop on top of a standard incremental SAT solver. And as we shall see, it yields a surprisingly good performance, but it's incomplete. So you cannot use it as is. You need to integrate it into some kind of a flow, which has other ways to improve the best model, to advance, to progress. Now, there are two techniques which we are using to improve Polosat. One is using a conflict threshold of 1000 for every SAT invocation. That's because we don't want to get stuck in bad SAT invocations. We prefer to go to the next one because there are many of them. And there is another technique called mutation combination, which essentially finds additional potential models based on an idea implemented in the quick sampler algorithm for SAT sampling. I'm not going into details here. Please refer to the paper. And now we can move on to experimental results. So integrating Polosat into an anytime Maxat solver is quite simple. We have done it. We have integrated Polosat into the winner of Maxat Evaluation 2019 in weighted incomplete categories TT Open WBO Inc. by just replacing SAT invocations by the strictly monotone Polosat invocations. So that's it, except that we have also used the so-called adaptive strategy. We figured that it helps to stop Polosat whenever the number of models per second gets slower than one. So whenever Polosat gets slow, it makes sense to stop it and fall back to the original algorithm. So that's the integration of Polosat into TT Open WBO Inc. And here are the results. We used 297 benchmarks from the Maxat evaluation, and we applied a timer of half an hour. Now you can see here the results for a number of solvers. On the x-axis we have the time. So the time goes from 1 minute to half an hour. And on the y-axis we see the score. So whenever the score is closer, the closer the score to 1, the better, essentially. The solvers we used include the following ones. So here the blue solver is TT Open WBO Inc., the baseline solver for our implementation. The red solver is the Polosat implementation in TT Open WBO Inc. And then there are two intermediate configurations here. No comp applies Polosat without mutation combination, and no CC applies it without conflict threshold. And the green solver applies Polosat without adaptive strategy. And we also ran Loandre, which is the runner-up at the Maxat evaluation. Now one can see that Polosat helps, right? The red plot is above the blue one, so it helps for every timeout. It's really helpful. Another interesting observation is that the adaptive strategy is required. So the adaptive strategy actually without the adaptive strategy, Polosat performs worse than the baseline solver, and that is because although Polosat without adaptive strategy is better for the majority of the instances, there are 19 instances on which it performs really, really badly. Polosat without adaptive strategy, but then when you turn it on, then the performance is fixed and everything is fine. And the contribution of conflict threshold and mutation combination is helpful, but marginal, as one can see from the graph. So that's it. And now we move on to the integration of Polosat into our industrial placement application. Let me now tell you a bit about the placement problem. On the left-hand side of the slide, you can see various stages of chip design. And one of the stages is called the physical design, where you need to place transistors and connect them, that is to route them. And the placement is an important sub-stage of the physical design stage of chip design. Let me present you a simplified version of the placement problem. On the input, you have a bunch of rectangles, and you need to place them as close as possible. So you need to place them so that the enclosing rectangle has the minimal possible perimeter. That's the essence of the problem. This problem is already in P-complete, but in practice it's more complex than that. There are multiple nets, and the optimization criteria is more complex. You can refer to the paper for more detail. And there is also a bunch of additional constraints: alignment, parity, minimal distance between rectangles. There are some keep-out regions, etc. In practice, the places are mostly heuristical in the industry, and these places scale to big designs, but they might violate some of the constraints, so they are not guaranteed to be clean. And also, if one has to change the constraints because something changed in the outside world, then it's not trivial. You need to change the tool itself. So a scalable SAT-based solution would have been really helpful. But it's really, really challenging to design one which works fast enough, which is efficient enough. Let me quickly remind you what optimization modular bit vector is about. So on the input, there is a bit vector formula. So we have bit vector variables, bit vector constants, and some bit vector expressions, assertions. And then one can either solve the formula or solve it and guaranteed that some bit vector is minimal. So in this particular case, on the left-hand side, we have a solution, and on the right-hand side, we have a solution which guarantees that U is minimal. So that's the problem of OBV, optimization modular bit vectors. And the placement problem can be reduced to it as follows. We associate two bit vectors with every rectangle. These bit vectors represent the bottommost corner for each rectangle. And then there are also the constant width and the constant height. And to find a solution, we just need to ensure that there is no overlap between the rectangles. To do that, we have this formula. And what it says is that essentially I is to the left of J, or to the right of it, or to the bottom, or to the top. And that's it. We ensure that there is no overlap. We also need to ensure there is no overflow, but I skip the exact formula here. And in order to find an optimal solution, we need to define an expression for the perimeter T. And you can see the expression here. So we take the maximal x value minus the minimum x value plus the maximum y value minus the minimal y value. And that's essentially it. We can also double it, but it doesn't matter in order to find the perimeter per se. But this is our optimization target T in this case for the OBV solver. In order to solve the placement problem, one can apply an existing off-the-shelf OBV solver. The best solvers work by reduction to multiple SAT invocations. So the best algorithm is Anytime. But unfortunately, although the SAT solver finds the initial solution rather quickly, at least in vast majority of the cases, it gets stuck at the optimization stage. So existing OBV algorithms do not scale to placement. The problem of placement can be easily reduced to OPSAT. The no overlap constraints can be reduced to CNF, and then we can define the objective function psi to simply return the value of t, the same t used by the OBV algorithm. Please notice here that psi is not a linear pseudo-Boolean function because the variables are bit vectors, that they are not Booleans. So here we show that Polosat is helpful in an industrial application, optimization application, where the function is not a linear pseudo-Boolean function, which I believe is quite interesting. We implemented a simple linear search algorithm for solving placement and integrated Polosat instead of SAT there. We found no audit in adaptive strategy. Here are the results. So we ran the default tool and the tool with Polosat on 156 industrial benchmarks with a half an hour timeout. The score goes between 0 and 1, where 1 is the score of the default tool in 24 hours. And again, we ran the default tool against the default tool plus Polosat, and one can see that Polosat makes our tool substantially more efficient for every timeout. Here is a head-to-head comparison. We have the default tool on x-axis and the Polosat on y-axis, and one can see that Polosat improves the performance for the vast majority of instances. Moreover, it makes the score bigger than 1 for a large portion of instances over a third of the instances, which means that it achieves a better performance in half an hour than the default tool in 24 hours, which is again quite impressive. And I can tell you that Polosat is an enabler for productizing the placer at Intel. It's time to conclude my talk. So I presented I defined the problem of OPSAT, optimizing a generic pseudo-Boolean function given a CNF formula. I presented a Polosat algorithm for solving OPSAT, and in the experimental result section, I showed that integrating Polosat into existing optimization flow is beneficial, including improving the state of the art in anytime OPSAT solving and enabling a placement application at Intel. That's it. Thank you for your attention.